Good day to all the judges. My name is Komin Jun, and along with my teammates Teng Shi Hong and also advisors Dr. Yo Pen Chin and Dr. Lim Boon Kian from Multimedia University Malacca campus. Our topic is regarding the development of 4 DOF SCARA robots with web-based control and monitoring system. So for the problem statement is that we all know that during the past industrial operations that the pick and place and all the others operations were performed manually by the humans, and which is time consuming and also involve risk factor. And we all know that nowadays internet is becoming center of everything, and also the COVID-19 has accelerated the adoption of the new technologies such as the IoT. So this problem statement leads to our deep topic, which is the development of robotics arm with web-based control system. So based on the research, the current solutions, the Raspberry Pi is widely used to develop the web-based control system for robotic arm at low cost. And also servo motors are used to act as the robotic arm actuators, along with the drivers connected directly to the GPIO of Raspberry Pi. But the limitation of the low price servo motor is that it will be unable to achieve the high accuracy, and also it will be very too heavy for Raspberry Pi to handle both uh, client and also the robotic arms. So this lead to our solutions. We replace the servo motor with stepper motors, and we add one more microcontroller which is called the Arduino Uno to our projects. And also we have been implemented the belt system for our rotational movement. So why? Because the stepper motor will be having the higher resolution and accuracy. And then by adding one more Arduino Uno, we can reduce the workload of the Raspberry Pi. And finally, with the belt system, we can increase the flexibility of them, such as the maximum payloads based on the belt system, the reduction ratio. So here comes to the demo and also the user feedbacks. So first is the manual control. So users can control the absolute impulse of joy controls by sliding the joy's bar. And then for the coordinate control is that users can enter the coordinates of the end factors in order to get the real world results. And the gripper control is for gripper to pick and place, meaning to grip and also to release. And then we can also use the pause button to pause the robotic arm and then create reset to move the robotic arm back to the guided. Or we can also use the stop all button as an emergency button to stop all the process, no matter in which state. So for the path planning is that we can record the operation of the robotic arm by, by creating a new task so that we can run the button, we can run the robotic arm and then record all the operations as a one whole pick and place operations. So after that, we can create the new pick and place operations by saving it and then back to the manual control page to execute it again. So from the real time video feedback, you can see that the robotic arm is doing the same operation as recorded just now. So this is the demo of both images. So for the target segment and also the impact, our target segment will be the small and medium size of enterprise SME. And for example, it can be the smart grocery, and also will be implemented in educational institutions for the students to have knowledge of the robotics based on the robotic arms. So for the part 2, the technical presentations, first talk about the overall system block diagram. The left side showing the overall system of our robotic arms, meaning with along with the two controllers, Raspberry Pi and Arduino Uno. All the components from the robotic arm will be connected to the Arduino Uno, and then for the Pi camera will be connected to the Raspberry Pi. So user will be able to access the Arduino Uno, meaning the robotic arm, with a web-based web page, uh, provided that the internet is connected to Raspberry Pi. And then for the overall system flowchart showing in right side, first we be able to access to the robotic arm with a specific IP address. After login to the robotic arms, we can the robotic arm will first back to the home positions and then wait for the command afterwards. For the hardware technology, we've been using the 3 revolve joint and 1 prismatic joint in develop our manipulator controller. And the right side showing is the actual model of our SCARA robots. So this picture showing the circuit diagram of our overall system, meaning that Raspberry Pi and Arduino Uno are connected with a serial cable, and all the drivers and limit switches and also the servo motor are connected to the digital pin or the analog pin and also the power pin to the ground pin to the Arduino Uno. And then for the software technology, the left figure shows the software system architectures involved of 3 modules: the web browser, the embedded server, and also the embedded device. So for the front end, we've been developed the front end user interface with HTML, CSS, and JavaScript. And then for the server, we've been developed the framework with the Flux framework in Python. And then for the embedded device, we've been developed the script with the embedded C and C++ in Arduino IDE. For the remote client module, the most important page we develop will be the manual control page, also the point-to-point power plant page. So the right side showing the layout of manual control page and layout of the power plant control page. So for the manual control page, it will be for users to direct control the robotic arm along with the live streaming. And then for the power plant is for users to record the running commands and also save to the database in order to execute later on. For the embedded software module, the left figure shows the code structures and the middle shows the communication protocol. As just mentioned just now, there will be a communications between the front end to the embedded system. Then it will be achieved by using the HTTP protocol. And then for the database configurations, we've been using the SQLite to develop our database, and there will be two information, the user and also the command. For the kinematic analysis, we have been doing it for the in order to get the formula for different target data. The lower tables shows the formula for the direct kinematic analysis and inverse kinematic analysis respectively. For the embedded device module, the left here shows the conceptual state machines diagram that we use to develop our program, our algorithms. And then for the right figure shows the flowchart of embedded device module, means that whenever after the robotic has back to the homing positions and then move to the idle state, then it will wait for the commands. If the command is available, then it will pass the command string and then try to execute it based on it. If no, then it will stay within the idle state. For the result discussion, this picture shows the uh, graphical user interface that developed by us. As you can see, the left figures showing that the embedded live stream are showing in the lower sectors. We've been doing the kinematic analysis for both direct and inverse with pick and place operations. For the trial one, we've been using the choice control and then compare it with silent simulations. Afterwards, it has been proved that the real world result and silent result are the same, and meaning that the direct kinematic analysis are correct. And then for the inverse kinematic, we've been using the coordinate control, and then also the real world result and so the silent result has been proved to be correct. Finally, move on to the specifications. The upper left figure shows the XY working envelope and the lower showing the repeatability. And finally, after getting all the required information, a specification table has been generated.
The benefit of our product is are low cost, lightweight, and eco-friendly, capable in areas that require light pick and place operation, such as smart grocery, and the web-based system allows user to control and monitor the robotic arm remotely. Thus, robotic arm can work 24 hours without the presence of user beside the robotic arm. Next, here will be the project demo. Right. In conclusion, the developed web-based control and monitoring system is verified by comparing the defined controls and the real-world result and simulated result. In future, we recommended that our project has to be implement machine learning or object detection. Thank you for watching and have a nice day.